Hello, I'm Yoichi. I work at zkSecurity now. I have some reputation about wearing things on stage. I think that's how you get invited to events. This is for the beast mode. Uh, the beast mode is not a furry thing, trust me. I will talk about formal verification. I will make very specific suggestions based on the current events. Formal verification is about getting correct software implementations, but the scenery is changing because computers have started writing mathematical proofs that check proof assistant that passes the checkers in the proof assistants like Lean. This trend has hit the headlines so far in the pure mathematics only, but similar techniques can be used for program verification as well. So this has changed the economy of getting correct software implementation, and I'll tell you about this. So this talk is mostly about having ways to check that your software implementation does what you expect. Not necessarily, not everybody needs to check all the software you use, but there has to be an accessible way to do that. This is a sovereignty thing. Open source is one component, so you have the source code that helps, but usually the implementation is so big that you don't want to read it all. And even after you read it all, you don't get much confidence because it was just too big. So I will be talking about strategies to make the situation better. To be honest, the amount of efforts will never go to zero, and you don't get an absolute guarantee. But I'll talk about the best way that seems to work currently. I've tried the method I'll be presenting, and that's the only edge I have. I did something like this 9 years ago in Paris. That was also in an theorem conference that some of you attended. I talked about formal verification of Ethereum smart contracts. So I was saying that the EVM is so simple that you can prove programs correct and that's useful. That was in February of 2017. And after several months, EVM, the Ethereum virtual machine, was specified in a formal verification framework called K framework. The spec is called KEVM. It is still being developed and used by a company called Runtime Verification in some parts of the activities. Another company called Cetora was founded a year later, and they are also developing and using a formal verification tool for EVM smart contracts. People from both companies are around if you are attending this offline, so you can talk to them. I have not been involved in these companies directly, but the thing is I called the technological trend, right? And I'm going to make another prediction at the end of this talk. But I'm going back a little bit. Here's a title of a talk in 2003 by Leslie Lamport. Leslie Lamport got Turing's Award for distributed consensus work, and that's being used, that line of work is being used in the consensus layer of Ethereum today. The title of the talk was The Future of Computing, Logic or Biology. These are two ways of dealing with computer systems. One is logical. Logic starts from the first principles and use deductions to get the properties that you want of your system. biology, the other way is biological. Biological approach is used when the system is too complicated to understand. And Lamport noticed that words like viruses are used in computer attacks. So like he noticed these biological ways are creeping into computer science. Lamport's talk starts like this. In the late 60s, Freud and Hoare discovered the concept of program correctness. Some people initially working on program correctness thought that in the future, everyone would prove that their programs were correct. Programming errors would then disappear. And this has not happened. After 50 years, there are still bugs. Why aren't people proving their software correct? There was a blocker until maybe October last year, why people didn't prove their software correct. It was just number of person years. Look at the examples, like there's a proven correct C compiler called CompSat. It took 3 person years until the first version. There are people doing formally verified compilers, but nobody has ever created a proven correct C++ compiler, or nobody has made a proven correct Rust compiler. So many major languages don't have proven correct compilers. There are people building a proven correct compiler for Viper, a smart contract language, and I think you can hear about this after this talk in another stage. But it's not yet the mainstream common practice. Another example is proven correct hypervisor. Hypervisor is a small operating system that can run multiple virtual machines on top of it. There's a family of hypervisors called L4, and there's one formally verified one called SL4. It took 22,000 years of efforts to implement and prove it correct. There is an ongoing effort to port this to other machine architectures and maintain it and so on, but it's a massive effort. The situation changed greatly last year. I just took this from a video, but this is a slide from Harmonix Alex Best. The talk was done last year in December. Harmonix is a company providing an AI agent that can turn math papers into proofs in Lean Proof Assistant. And there are hobbyists and mathematicians who are using Harmonix tools to check mathematical results in the proof assistant Lean. This can help expanding the boundary of human knowledge. But when I think about program verification, the usual proofs in program verification is much simpler, much more repetitive than contemporary math. So I have an answer to this question. Computers can prove theorems. What's next? One of the next things is to use this new theorem proving ability to check the software correctness. There's another company called Math Inc. This company is also developing AI agents that can help translating math results into the Lean Proof Assistant. Here, we are seeing posts about a world of mathematical abundance, or in the limit, formal verification will be too cheap to meter. Math Inc. has chosen a careful formulation by saying in the limit. I'm showing you that there are businesses doing automatic theorem proving, and they are very confident that the technology will be cheaper. I tried some AI tools and coding bots and Aristotle's Harmonix too. These tools are already useful for writing proofs about software implementations. This changes the economics a lot, but we have to be careful. This is not the end of my talk, just half. When something gets cheaper, something else becomes the new bottleneck. So let's step back a little bit and see what can be the bottleneck. This is a whole picture of formal verification. The aim of formal verification is to make sure that the reality matches the expectation. But so whichever tool you use, you need to describe the reality using the tool and the expectations in the tool as well. Those descriptions are called models. I don't like the choice of the word here. So models usually look like just program code. Sometimes they are logical formulas, sometimes they are programs. But anyway, the models in a reasoning tool is code. The models need to be accurate for the whole process to be useful at all. So now, what's getting cheaper? What's getting cheaper is this comparison of models in the reasoning tool. That's getting cheaper. So the new bottleneck is somewhere else. So what are the bottlenecks? The biggest thing you can control is the choice of the reality you choose, you reason about. I don't think the real world as a whole is a good target of formal verification because the totality of the real world is messy enough. That's too messy. So the reality you choose, the domain of reality you choose first needs to behave with some predictable regularity. The reality can behave deterministically or non-deterministically, but even if it's non-deterministic, the set of outcomes needs to be known in advance for any logical reasoning tools to be useful. Another thing is the choice of the expectation. If the expectation is written in a language that requires a judge to interpret, it might not be a suitable problem for reasoning tools. So here's a problem. Maybe this is the most important thing here. So there are very popular programming languages like C++, or there are popular CPUs like Intel's CPU or ARM CPU. These things have sometimes thousands of pages of specifications, like modern CPUs have tens of thousands of pages. So if somebody translates these big specifications in a proof assistant and tell me this is the specification of the CPU, then first I don't trust it, and I don't want to read through all the 10,000 pages and compare that with some code either. And even if I do that, I will have a very difficult time convincing other people that this is the translation of that big thing. This will be the biggest bottleneck. So my goal here is that everybody can learn and put reasonable efforts to check that the programming language is described correctly in a proof assistant. So we have to watch out the complexity of programming language. So we need a reality with lean interface. I will show you some good examples that seem to work. The first example is the theorem virtual machine, the EVM. EVM is simple enough. And from very early days, the EVM has multiple implementations, and they have been compared against each other on the real network, test network, and using the test suites. So when you create a new model of EVM or implementation of the EVM, you can compare your model against the actual implementations using many ways. And that helps a lot. But there are already like professional companies doing this, so I don't go into much details. The thing with EVM is the expectations are a little bit difficult. Like there are many different kinds of attack situations that you have to be aware about. So writing the correct expectation for EVM smart contracts is not very straightforward. This requires domain knowledge and oversight. The second example is the arithmetic circuit for succinct arguments or zk proofs. Here, the reality consists of polynomial equations, and the proof assistants know a lot about polynomial equations already because people have been doing mathematics on proof assistants. Also, people use arithmetic circuits for like hash function or virtual machine or something that can be described mathematically easily enough. And after that, you can benefit from the coming mathematical abundance. zkSecurity is doing a project about this called Clean. It's supported by the Ethereum Foundation. Other teams are doing similar efforts, so this area is popular right now. The last example I have is RISC-V. RISC-V is a CPU architecture. It's very simple. Maybe it's simpler than EVM. So it's possible to implement or specify RISC-V in a proof assistant. It's better yet because the official RISC-V specification has been translated into Lean, and this has been also supported by the Ethereum Foundation. And once you code up your expectation of what your RISC-V program would do, like maybe the Ethereum virtual machine, then you also benefit from the coming or already existing mathematical abundance. I'm doing a project about this, it's called EVM ASM. And this might be useful for the beast mode Ethereum. It's a way to, it's a proposal to scale Ethereum using the succinct arguments. I promised I'll make a prediction. My prediction is that there's a new stack of proven correct software. It's Vibe coded assembly plus Vibe proofs on proof assistants, Ethereum provers. And this will be useful for system programming, operating systems, cryptographic implementations. EVM ASM is our first good goal, I think. I think this approach will spread to wider area of software development. That's all. Please ask me questions.
Sorry, just first of all, thank you very much. It was a really fun talk. For this last point, can you elaborate a bit more on what your stack looks like here? If you can, of course. How much of this is custom? How much of these tools are tools that will be available to others? Like, what's your balance? Do you think general purpose models would, for example, work well here, or do you need to do your own fine-tuning / your own stack building?
So this combination, like writing assembly code and proving them in a proof assistant, has been around for maybe 4 decades or something. And so when I started this EVM ASM project, I told the coding bot to like give me a RISC-V program verification framework and have a look at this paper. And it did that. It made some mistakes, but the separating conjunction or separating logic should be separating, but it was not separating or something like that. But once I tell it to fix the mistakes, it was also already useful. So at the moment I'm doing it in a very custom way. I mean, that's a way to get a very simple setup. But probably as this approach gets popular, things will be standardized a little bit. Yeah, I guess it's about to be time. Maybe one quick question is possible, maybe not. Last chance, I think. Thank you very much.